Assalamu alaikum dear students. How are you? I'm your instructor Muhammad Ali Musawir from UAT Lahore New Campus, and this is the lab course of analog and digital communication. And today here we will study about AM modulation and demodulation. So let's grab the concept first of all. What is amplitude modulation? Amplitude modulation is actually a technology which mainly use the radio carrier wave messages and transmit it over a modified signal. Let's understand the concept actually. What is happening here? Suppose this one is our message signal, and if we talk about the real world, the message signal varies from uh, maybe 500 hertz to 3500 hertz or 4000 hertz. Okay, so in real world the message signal, the speech signal which we actually have, it varies from 500 hertz to 3500 hertz. But here in the labs, in the experiment, we will use 1 kilohertz as a message signal, and 1 kilohertz is what it lies in between, it lies in the speech signal. So we will take this 1 kilohertz and use this one as a message signal. So here this one is our message signal. You can see 1 kilohertz of a sinusoidal wave. And the other thing we have the carrier wave. What actually happens here? Actually, we have to convert this low quality message signal, or I can say low frequency message signal, which is 1 kilohertz, low frequency message signal into a high frequency with some modifications so that it can travel far enough and we can deliver our message far away. I hope you got this concept that what is modulation, what is this thing, and how it works. We actually converts our low frequency message signal into a higher frequency message signal with some modifications so that it can go farther and we can deliver our messages wirelessly. So what actually happens here, we mix our this message signal, this is our message signal, we mix our message signal with a known higher frequency signal which is known as a carrier signal. So this is our message signal. We mix this message signal with a known higher, or I can say very high frequency signal. Okay, this one to get a modulated signal, and this modulated signal will be transferred wirelessly from the transmitter to the receiver. Okay, so what actually happens in amplitude modulation, the amplitude of the wave, okay, the amplitude of the wave changes, and we will encode or decode it accordingly, and we can extract our original message signal. Let's see how this thing goes. First of all, here we have this original message signal. Okay, this is our 1 kilohertz frequency. This one is our carrier signal by which we will mix the message signal into it and we will obtain the modulated signal. So this is our message signal, this is our carrier signal. We will mix these both to obtain the modulated signal, and then we can transmit it over the transmitter or antenna. In amplitude modulation, the amplitude will change. First of all, this is our, I can say, midpoint. Okay, the line, the zero line, the zero amplitude line, the reference axis, it is our midpoint. Okay, okay, and The upper point, I can say the peak point will have the highest amplitude on the in the modulated signal. The lowest point, this is our lowest point of the message signal. The lowest point of the message signal will reflect the lowest amplitude in the modulated signal. Okay, the frequency of this modulated signal depends on sorry the the frequency of this modulated signal depends on the carrier signal. The frequency remains same as the carrier have. If the carrier has a frequency of, let's say, 1 megahertz, then the modulated signal will also have a frequency of 1 megahertz. The only change we will see here is actually the amplitude of this carrier signal. You can say that we will have the same carrier signal, and only the amplitude of this carrier is changed according to this message signal. This is actually called the amplitude modulation. All right, so it changes according to the message signal's amplitude. I hope you got this point, that the amplitude modulation is nothing else but the variation of amplitude, okay, on the carrier signal, okay, by the message signal. I hope it's clear now. Okay, now we'll see the types of it. We will have different types of I can say bands. uh, Here you can see that we have amplitude modulation, and what we have actually, I just said that we have to shift the low frequency signal into the higher frequency signal. Okay, so what are the types here? We can say that we have a double sideband, suppressed carrier, then we have a single sideband. You can see this is the zero frequency. Okay, this is the real frequency axis, I can say, and this is the conjugate of it, or I can say imaginary values. Anyways, first of all, if you take the example here, if this one carrier signal, if it is of 1000 hertz, let's say, if the carrier is of 1000 hertz, then in the double sideband transmission we will have a carrier signal, the upper signal, and the lower signal. Let me explain this thing. What actually happens here? You actually add the frequency of the message signal and carrier signal to obtain this upper sideband. You can subtract the frequency of this message signal from the carrier signal to obtain this lower sideband. So what actually happening here, to shift the lower frequency into the higher frequency, we just have to add the carrier signal and the message signal, or we can say that we have to subtract the message signal from the carrier signal. Okay, this is how we obtain our higher frequency, uh, you can say our higher frequency signal. We just have to add or subtract the frequency of the message signal from the carrier signal. Okay, so If we have a double sideband, it means that the modulation is in such a type that in the modulated signal, in the signal which we have to transmit, this contains the transmission signal contains here the carrier signal, the sum of carrier and message signal, and the difference of carrier and message signal. This is called a double sideband. Okay, so double sideband is nothing else but a carrier signal, okay, the addition of carrier and message signal, and the subtraction of carrier and message signal. This is called a double sideband. So actually, you can say that let's suppose that if this one is of 100 hertz, let's say the message signal is of 100 hertz and the carrier is of 1000 hertz. So the signal which we have to transmit, it actually contains 1000 hertz, okay, 1000 plus 100, 1100 hertz, and 1000 minus 100, which is 900 hertz. Okay, so our transmitted signal, our the modulated signal actually contains the 1000 hertz, 1100 hertz, and 900 hertz. This is called, if the transmission signal, if the modulated signal is such a type, then this is called a double sideband. And actually it is what? It is actually just the frequency spectrum of a double sideband. Now in some cases we actually cancel this carrier signal because it actually contains no information. Okay, you can say that actually all the information is stored in the upper sideband or in the lower sideband. This carrier signal contains no message. So if we cancel this, or I can say if we suppress this carrier signal, then this is called a double sideband. This is the lower sideband, this is the upper sideband, and the carrier is suppressed. So this is called the double sideband with suppressed carrier. Okay, so if our modulated signal is such a type where the carrier is suppressed and we have the upper sideband, and if we have the lower sideband, then this is called a double sideband suppressed carrier. Alright, now let me also tell you that in the upper sideband and in the lower sideband, both contains the same information. The same information is present in the upper sideband as well as in the lower sideband. So if we cancel one of the sideband, because both have the same information, we don't need a copy of that information. So if we just uh, suppress that single sideband, also means if we just keep our one sideband upper or lower is your choice, and we suppress the other sideband, then we will have a single sideband. And if we have a single sideband in our modulated signal, then it is called a single sideband modulated signal. Alright, I hope you got that thing. Okay, you can make now I'm talking about the according to the real world, how you can make this. You can produce a double sideband, okay, in which we have a carrier signal, the upper sideband and the lower sideband. So you can produce a double sideband with the help of transistors and with the help of diodes, and nowadays you also have ICs. But actually double sideband is not efficient because you can see we have carrier signals and we have you can say that here the energy loss is very much, so we actually turn to use this double sideband, and we actually use a single sideband because here we have a shorter bandwidth, and the energy efficient method is also single sideband, so we usually use single sidebands. Anyways, So if you want to create, if you want to produce a double sideband, you can use transistors and diodes. All right. Because how you can do this? Because what does the transistors do? Transistors, you know that transistors amplify the wave, the signal, the input signal, okay? Amplifies the input signal. So what actually a transistor do? Transistor controls the amplitude of this carrier signal according to the input of this message signal. So the amplitude changes according to the message signal, okay, and changes to what signal? You can say that the amplitude of the carrier signal changes according to the amplitude of the input signal. This is how transistors are used in this double sideband production. All right. Now, if you want to produce double sideband with suppressed carrier, how you can do this? You can see this is a block diagram of this thing of the production of double sideband suppressed carrier. You have to use the AM modulator. What is AM modulator? AM modulator is actually a double sideband producer. So this thing, the double sideband, you can take this double sideband and put it in this block. You can imagine that this block is actually nothing but a double sideband producer. You have a double sideband producer, you have a double sideband producer here also. Here we have our message input, and here we have our carrier input. So what actually happens here? Message signal goes in, okay, carrier signal goes here, and what happens? It produces a double sideband here. Means this signal produces this signal on this line. The S1 signal contains this type of modulated signal. Similarly here, the message signal goes here. It is a 180 degrees phase shifter. Means it shifts the angle of the message signal, because here the input is message signal. So a phase shifted message signal goes here, carrier comes from here, and here also a double sideband is produced, but with a different, you can say, with a change of 180 degrees shift. And here it goes, and here we have a summation which actually cancels the shifted value. Here we have a signal with 0 degrees, here we have a signal with 180 degrees. So here actually 0 and 180 degrees cancels the carrier signal, and we will have a double sideband suppressed carrier here, right? And if we talk about a single sideband production, we will just have this product modulator. It is the balance modulator, okay. Okay, this function, this thing is called a balanced modulator. You can also use a ring modulator, in which a ring modulator is actually nothing but you can do this by using a diodes, okay. So this is a balanced modulator, and to obtain a single sideband you have to put this balanced modulator here, okay. If you put a balanced modulator here and here, you can observe that here comes the message, here comes the carrier signal, and here we have a double sideband suppressed carrier. On the other hand, we will have a 90 degrees phase shifted message signal, a 90 degrees phase shifted carrier signal, and then we have a double sideband suppressed carrier here. And then we have the summation, and we will obtain a single sideband. Let me tell you that if we add here this signal and this signal, we will obtain the upper sideband. You can see here that here we have two sidebands. So if you add these two signals, you will obtain the upper sideband. But if you subtract one of them, you can see that here, if we subtract these two, we will obtain the lower sideband. So if you want to obtain the upper sideband, you have to add these, and if you have to obtain the lower sideband, you have to subtract these. All right, I hope you got that point. Now this is the diagram. Here in the time domain, the double sideband modulated signal looks like this. Okay, and in the frequency spectrum, it looks like this. If we have a double sideband suppressed carrier signal in the time domain, it looks like this. In the frequency domain, it looks like this. If you talk about the single sideband, upper or lower, it looks like this. You can see it looks very much similar to a simple sinusoidal wave, but it is actually not. If you observe closely, you can see here that one is higher, one is lower, one is higher, one is lower. Okay, so in the time domain, single sideband modulated signal looks like this, and in the frequency spectrum, it looks like this. All right. So in the real world, how can you do this? The balanced modulator is actually built in ICs, and here I am going to discuss one of the IC. Here it is MC1496. It is an IC which actually contains the circuit of a balanced modulator. So we have to input the sorry, here, what is this, the message signal. We have to input message signal, we have to input the carrier signal. Okay, and in the output we can obtain a double sideband suppressed carrier, or we can obtain a single sideband. How can you obtain this? If you have a double sideband suppressed carrier, you can just add a what you can add a filter. You can add a notch filter which can filter out the frequency which is not required here, so you can eliminate the upper or lower band. Okay, this is one of the method, means you can use a balanced modulator and the result will be a double sideband suppressed carrier, and then you can use a filter to obtain a single sideband. And the other process to obtain a single sideband was to use this thing. This is actually nothing but a phase modulator. Okay, the first method to obtain a single sideband was to use a balanced modulator, and then you can add filters. And the other thing you can do this, you can use a phase shifter to directly obtain a single sideband. All right, so here it is a balanced modulator. If you add a notch filter in such a way that it can eliminate one of the sidebands, so you can get a single sideband. Or if you want to obtain a double sideband, you can obtain a double sideband also. Okay, so if you think up in your mind what you can do here, you can actually add some filters so that you can take only the frequency between 500 and 3500 hertz, because this is the information. We actually have the information between this range. Okay, and then you can also put a filter here in the carrier path so that it filters out the frequency. If there is noise, it can filter it out. Okay, and then after doing some biasing, you know what is this, after doing some biasing, okay, you can add some filters on the output side also, and then you can obtain your output accordingly. All right, okay, so it is till now we have studied the amplitude modulation. Now we will see its practical on the oscilloscope, and we will understand what it actually looks like in a real world. Then we will move on this AM demodulation, how to demodulate, how to extract the original message signal from that modulated signal. All right, so let's go ahead on the practical decks.
Okay, students, this is the message signal that we have, and if I show you the carrier signal, it will look like this one. So this is the carrier signal. It is a pure sinusoidal wave. If I change the time per div, you will see a pure sinusoidal wave. Okay, if I show you the modulated signal, it will look like this one. This is the modulated signal that we have. So why it is fluctuating? Because in amplitude modulation the amplitude changes according to the message signal. If I change the time per div, you will see the modulated signal that we have discussed earlier here. So if I have just changed the time per div here. All right. Okay, now if I stop this wave to see what is actually here, it will look like this one. So you can see that here we have some high amplitude and some low amplitude here. You know that the low amplitude is the place where the amplitude of the message signal is low. Okay, so this is the amplitude modulation. We have completely done this. So let's move towards the amplitude demodulation. First of all, I will tell you the concept, then we will move its practical.
Alright, students, now let's discuss amplitude demodulation. So, first of all, you can say that if we have different modulated waves, then their demodulation will also be of different type. If we have a double sideband modulated signal, then its demodulation will be of different type, and if we have a double sideband suppressed carrier or single sideband, then its demodulation will be of different type. The process will be changed here. Alright, I hope you got it. If we have this double sideband signal, then the modulation will of different type, will be of different type. And if we have a double sideband suppressed carrier or a single side, then the process will be different. Okay, if we have a double sideband, then the demodulation will be held by using the process which is called rectifier bridge. We will do bridge rectification, and then we will be able to convert the double sideband signal, means the modulated signal, into the demodulated signal, means we are obtaining here the original message signal. And if we have a double sideband suppressed carrier or a single sideband modulated signal, then we will use balanced modulator for its demodulation. Now some of them might be thinking that balanced modulator earlier was used in the modulation technique. Okay, it was the balanced modulator, and we have produced the double sideband suppressed carrier also with a single sideband with the help of this modulator. Okay, one thing I forgot here, that the single sideband can be produced by the balance modulator plus filters and the phasing method. This is not phasing modulator. That's my mistake. This is not the phase modulation. It is actually the phasing method. Phasing modulation is something else. It is used in uh, frequency domain, means where we have the frequency modulation and demodulation. Okay, so here it is not frequency, it is not phase modulator, it's phasing method. All right, anyways, so the balance modulator was used for the production of double sideband suppressed carrier as well as for the single sideband. You can see here we will use here this same balance modulator to demodulate the double sideband suppressed carrier, also the single sideband. Right. Now let's discuss this. First of all, we will discuss this double sideband in which we will use the bridge rectifier. This is the wave, means the time domain wave of a AM double sideband. This is an AM double sideband modulated signal, and it's look like this. In the frequency domain, it looks like this. You know that in double sideband we will have the carrier signal, the upper sideband, and the lower sideband. Okay, all right. So if we just pass this signal through a bridge rectifier, you know what is a bridge rectifier? A bridge rectifier actually converts this means an AC signal into a DC signal. You can see that this is a wave, and it is clearly observed. It can clearly observe from here that this is an AC wave because half part of this in the positive domain and half part of this in the negative domain. So this is an AC sinusoidal wave, and after passing this signal from a bridge rectifier, the signal will look like this. Here you can see that say that the negative cycles will be converted in the positive cycles, and the signal below zero will be erased. So all of the signal will be in the positive cycle, will be in the positive domain, and it will look like this. The negative part is converted in the positive part, and here you can say almost a continuous flow of the signal. All right, and if we pass this rectified signal from a capacitor, means not literally passing from a capacitor, means a capacitor can be used here to eliminate the ripples. A capacitor can be used to maintain the fluctuation, means to minimizing the fluctuation. And if we use a perfectly calibrated calculated capacitor, then the ripples will be minimum, and you can say that in the frequency domain we can observe clearly that here the original signal has a very much minimum magnitude, and we have an original message signal, means this signal contains this modulated signal as well as the original signal. So if we pass this signal from a filter, a low pass filter, then we can obtain our original message signal after passing this from a low pass filter. And you can see that the carrier signal, the upper sideband, lower sideband will be suppressed from here. All right, so this is the demodulation of a double sideband. It can only be done by bridge rectification method. Okay, and it is called envelope detector. And the balance modulator technique for double sideband suppressed carrier and single sideband, it is known as coherent detector, and it is also known as product detector. All right, okay. Now I will tell here if we have a single sideband, because it is used very much here. So if we have a single sideband modulated signal in time domain, it will look like this. In frequency domain, it will look like this. All right, so if we have a you can say that the modulated signal, AM single sideband modulated signal, how we can demodulate this? We can demodulate this by using balanced modulator. Okay, you know that balanced modulator, what it do? It actually produces two sidebands, the upper sideband as well as the lower sideband. If we have the message signal, because the input of, you can say, the input of a balanced modulator is called the message signal and the carrier signal. We have two inputs in the balanced modulator. One is the message signal and one is the carrier signal. If we consider this one as a message signal, then you can say that the frequency of this message signal is 99 kilohertz. The frequency of this message signal is 99 kilohertz, and let's assume that the frequency of the carrier signal is 100 kilohertz. If we have carrier frequency 100 kilohertz and message frequency 99 kilohertz, then we will obtain two frequencies in the result. By passing these two in by the balanced modulator, we will obtain the upper sideband, and we can get it by adding 99 kilohertz plus the carrier signal 199. Okay, so 199 kilohertz will be the upper sideband, and the lower sideband can be uh, obtained by subtracting 100 kilohertz minus 99 kilohertz. So it will be 1 kilohertz. So this is our lower sideband, the upper sideband as well as the lower sideband. And from here you can see that, of course, you can see that 1 kilohertz is what 1 kilohertz is actually our original message signal. And if we pass this from a filter, a low pass filter, we can obtain our lower sideband, which is actually our original message signal, and in the time domain it will look like this. Okay, so if we have a single sideband, it can be done by using what? By using bridge rectifier. And if we have a double sideband suppressed carrier or a single sideband, it can be done by using the same technique, which is balanced modulator. Alright, and here one more thing. The carrier frequency in the demodulation should be same as the modulation, as the carrier frequency of the modulation. So if the carrier frequency is not same, then you can say that our result, our original signal cannot be obtained correctly. There can be a difference between the original and the extracted one. Alright, so these are the two techniques here. I hope you got these. And if you look at the graph, if you look at the graph in the oscilloscope, then you will see correctly that what is actually happening here. So let's see what for a while.
Okay, students. So this was the modulated signal that we have. Okay, and you can see there is some noise. Okay, anyways, so this was the modulated signal, and you can see that this type of modulated signal is look like a double sideband suppressed carrier, because you can see that here we have some very low, you can say, in between gaps and high amplitudes here, so it looks like a double sideband suppressed carrier. Okay, so if I pass this from a demodulated circuit, um, we will see the original signal. Let me adjust some things. So after adjustment, it will move towards the original message signal. Wait until we got the original message signal. Okay, so here we have the original message signal. Okay, so this was our practical. Thank you.